सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै।
Hello and welcome everybody again to the lectures on computer graphics. Today we are going to discuss methods to represent solid objects. How do you represent solid object structures in this field of computer graphics, because we have to know methods by which we represent them or model them and then position them in the first stage of the viewing pipeline before we apply normalizing transformations. Objects which we see before us typically are both natural and artificial objects, and there are various methods by which these are represented. Depending upon the application, we sometimes need to represent solid objects, sometimes we need to represent soft objects also, but we will restrict our discussion today to discussions based on methods to represent solid objects. So, solid modeling is the discussion which is the title of the discussion today, and out of the various categories the most significant one being the constructive solid geometry or CSG. Okay. So, if you look into the slide, the various methods which are used to represent or model solid objects are regularized Boolean set operations, sweep representations, octrees, CSG or constructive solid geometry, which is also one of the methods of representing solids or modeling solids. Then B-reps or boundary representations, which we will see. I think mainly we will discuss this first 5 methods depending upon the scope and time available to us. There are methods of primitive instancing and fractal dimension, which I leave for users to read themselves, which are the fractal dimensions are methods by which you represent natural objects, structures, not necessarily solids. Okay. So, we first look into a method by which a solid is represented. Let us take an example of a simple cube. Okay. Let us take the example of a simple cubical structures, and which has 8 vertices as at the end points of the cube. 4 on the bottom, 4 on the top, or 4 on the left, 4 on the right. The corresponding vertices are A, B, C and D, E, F, G and H. And if we visualize that the vertex A of this unit cube means the length of the solid is unity, the length, height and the breadth. And if the vertex A is at the origin of the coordinate system, then the corresponding vertices, the coordinates of the rest of the vertices are also given on the left hand side of U. We assume that the line AB lies on the x axis, whereas the line AD or EH lie on the y axis, and correspondingly the line, let us say AE or BF, they lie parallel to the z axis. So, these are the 3 orthogonal axes on which the cube is lying, and the vertex A is at the origin of the coordinate system. So, based on this concept, you can visualize the left hand side table, which talks about the coordinates of the different vertices on the left hand side. So, a set of 8 vertices can represent a solid, in this case a cube, let us say. So, you have to store basically the set of vertices, and that is information sufficient in this case to represent a a cube. But let us say if we talk of an arbitrary objects, it is not always possible to represent the solid object structure with the help of vertices only. In this of course, you need to store vertices all right, but you also need to find out which of the vertices are connected by lines and which of the lines form a particular polygonal shape or a square shape in this particular case of a cube. So, let us know is connected to the vertex B at 1 0 0 by a line, correct. This, as you can see, there is no mention of the line joining vertices A and C, because it does not exist in the picture. Okay. So, you can see lines such as AC, DB, they do not exist on the right hand side column. If you count the number of lines, how many lines do you think exist in a cube? 4 at the bottom, 4 on the top and the 4 along the side. So, there should be 12 lines or 12 edges which exist in a cube, and you can count on the right hand side that there are actually 12 lines specified. So, these 12 lines tell you which of these vertices are connected. Okay. That is one way by which, another way by which the solid object also can be represented, and that means you not only need to specify the vertices, but you also need to specify the lines which connect the corresponding vertices. Okay. So, this is one way by which a solid can be represented with the help of vertices and lines, of course, but this is not a very complete representation. We need actually some more information in terms of trying to know which of these lines form an enclosed polygon. Okay. So, solid we know is bound by surfaces, solid is bound by surfaces. So, we need to also define the polygons of the vertices which form the solid. It must be also a valid representation. If you take any solid in front of you, let us say you take the furniture of a classroom, you take the chairs and the tables, and in some cases you have the board. You may have computer systems being used for practical laboratory classes, you may have apparatus, electrical or mechanical instruments being used. If you look at those artificial solid objects, typically any such solid object, preferably it is easy for you to visualize a box type of a structure or a cube for that matter, the most simplest case, it is always bound by surfaces. So, you need to actually on the top or level of representation define the surfaces which enclose a particular solid. Okay. And when you talk of surfaces, in this case of course, we are assuming very simplistic planar surfaces or planes which bind the particular solid, okay, any solid for that matter. And when we talk of planar surfaces or planes which bind, which constitute the surfaces to bound the, which bound the solid, then of course, you need the a representation to represent those surfaces or planar surfaces, and planar surfaces can be represented using polygons. Okay. Using polygons, we know that in the case of a cube, of course, the polygons were simply squares of unit length, but it could be any arbitrary solid which you can visualize, which should be bound by surfaces. And so, we need to hence define polygons with the help of vertices to which should represent a surface. So, let me again clarify that a solid is bound by surfaces. There are, let us say, m number of surfaces which bind a particular solid. Each of the surfaces will be represented by polygons. So, each of those polygons will have, let us say, n different vertices or lines which define that polygon. And since, as you have seen in the previous slide, that once you define the vertices, with the help of the vertices you can define the lines, okay, which join the corresponding vertices, and then you can pick up a set of lines or edges which constitute a polygon. Those polygons actually define the surfaces which bind the solid. So, I hope you can understand that at the top you are talking of surfaces, then the edges are lines of which define these polygonal surfaces, and then of course, vertices which define the corresponding line or the edges which join a set of vertices, a pair of vertices to form a line. So, at the very lower level you have vertices, then lines or edges, and then the polygonal surfaces to represent a solid structure, or you can look from the other way around from top to bottom. The solid structure is represented with the help of polygonal surfaces, polygons defined with the help of lines or vertices, and at the very low level you have the vertices which define these lines as well. So, if you look back, so I repeat these sentences once again, a solid is bound by surfaces. So, we need to also define the polygons of the vertices which form the solid. I hope this statement is very clear now, and of course, then we also need to check whether it is a valid representation of a solid, because a solid is bound Okay. There is no open space for a solid, but typically when we see a solid structure, so it should be bound by surfaces on all sides, left, right, top, bottom, front and back and so on and so forth. A cube is a typical example. We cannot visualize that a solid exists like a single plane. You cannot define a solid with a single plane, because it is not binding any particular volume, a solid volume or a structure. Okay. So, we will see methods by which we need to validate the representations of solids, and one such method we will see with the help of the first representation which we will look is the regularized Boolean set operations in solid. So, before we move on to valid representations or methods to validate, we will look into another representations of solids and methods by which you can create different type of solids from simple structures. Let us look at this simple example. Okay. Now, regularized Boolean set operations are of three categories. You basically define a set of operators which operates on solid structures, and the three operators which simply are used are called the union, intersection and the difference. The corresponding symbols are given on the right hand side. This is the symbol for the union, intersections. It is a simple set based operation, operations on sets, okay, and the difference between the two. Okay. So, Boolean intersections of say cubes, because we know actually right now that how to represent a cube at least, because we can define the cubes with help of about 8 surfaces. Each such surface will be defined with the help of 4 polygonal edges or squares. So, the number of the surfaces which you have, although are 6, the number of edges or lines which we have seen for the polygon are 12, and the number of vertices are also 8. So, remember these figures, this will come back. I repeat again, for a cube we have 6 surfaces, 12 edges or lines and 8 vertices. Okay. So, remember these figures, and with the help of once you define this cube, we will say that with these operations of union, intersections and difference, mainly the intersection, let us say of say cubes, you may produce other types of solids. You can also produce planes, lines, points and what we call as null objects, and we will see with an example what do you mean by this. Okay. Let us see some examples of regularized Boolean set operations, but we will just see the examples of Boolean set operations first, and then we will see what do you mean by the term regularization on these Boolean set operations. Okay. Let us take 2 cubes. Okay. The same cube which you have seen a couple of slides back earlier. Now, I have taken 2 such cubes. Each of these cubes are of the same size and dimension. They have, each of them have, I repeat again, 8 vertices and 6 surfaces and 12 lines, which constitute each of these cubes. Remember these values once again, and let us say there are 2 such cubes represented by 2 different colors of identical size A and B. Okay. If that is so, then we look at the intersection of A and B. Now, depending upon the position of A with respect to B, you will get different values of A intersection B. You have to visualize that this intersection can be obtained by placing this one cube within the other, where there is a overlap of one portion of the solid portion or the volume covered by A and also with B. So, the A intersection B which you are seeing is a common part of the volume occupied by both A and B, when A and B are not only placed adjacent, but one is a little bit inside the other. So, if both A and B occupy the same volume, that means they occupy the same space, then the intersection produces the same object. Now, if you start sliding one with respect to the other one and assume both A and B are in the same place, remember we are working in a virtual environment. Okay. Computer graphics is supposed to produce a virtual reality or a virtual environment, and although in the realistically in the true world in which we live, not in the virtual world, we cannot put one solid object within another one unless you have a vacuum inside. If you have a solid structure, say a rock or a table, we cannot put another object like a chair or a pen inside that where the surfaces intersect. It is not possible, but remember this is a virtual scenario, a virtual reality. We are living in a virtual world with computer graphics, and here it is possible to have one solid penetrating inside the zone of the other one. That is virtually possible. Whether it is valid or not, we will see later on, but right now assume that it is possible. So, if it is possible, let us say if A and B are 2 separate cubes as shown in the slide a couple of minutes earlier, the last slide which you have seen, if we place A and B in such a manner that both of them occupy identical or same volumes in the coordinate system. That means, we have one of the vertices at the origin of the coordinate system of both these cubes, and the corresponding 3 axes which come out of that particular vertex gets aligned with the x, y and z axis. So, if that is the case, then both A and B occupy the same position, and in that particular case the intersection of A and B will produce the same output. However, if we take B and start sliding it with respect to B along any of the one orthogonal axis x, y and z, then what will happen is, if we do not take the, of course, the B completely out of A, then after sliding a little bit, we will have some common volume which will be or some volume in 3D space, which will be not a cube but a rectangular parallelepiped type of a structure, which will be common to both these volumes A and B, common to both these A and volumes A and B, and this is the structure which is shown in the slide here. So, what I have done is basically put B on A at the same position and started sliding a little bit. The more you slide, lesser will be the width of this intersection, and when you have just slid a little bit and there is a huge amount of volume which is common to A and B, then the intersection volume also will be very, very large. So, you have to visualize this, that the intersection A and B is a common volume between both A and B. Now, if you keep on sliding it quite a lot, what will happen is, at some point of time A and B will be adjacent to each other. Adjacent means there will be just one common plane which is just common to both of the volumes A and B, and the common intersection actually could result in a plane. That means, depending upon the relative positions of A and B, these two solids, the intersection, which is also a solid output in general, will depend on the relative positions of A and B. Okay, the A and B, the relative positions dictate the intersection volume. I repeat, when A and B occupy the same place, you have the same output as the structure of both A and B. Start sliding, you start have intersection volumes like rectangular parallelepiped coming out. The more amount of slide which you give, lesser is the common volume which comes out, and at one point of time when both A and B are just adjacent, where there is just one plane in between the two solids A and B, you will have just, you have to visualize this, that you have just one common plane. It is possible that I can position A and B in such a manner that there could be just one particular line, there just could be one particular line common to A and B, or even one particular point common to A and B. Just one of the vertices could be shared or common between the two structures. Visualize there is an object A or a solid, in this case a cube, and I put another solid B of the same structure in such a manner that there is just one vertex which is common to both these volumes. So, depending upon the relative location of A and B, you will generally have intersecting solids, which is the common volume between these two solids A and B. You could have a resultant plane, you could have a common volume as a resultant line or a vertex point, or the other option is when two solids A and B are separated wide apart, where there is nothing common between the two, you could result in a, what is the common space which will be resultant? You will be having a null object. You can have a null object as an output when A and B do not share anything in common in terms of volumes, surfaces, lines or even points. So, that is what was the point in the last slide, in the statement which we made, that intersection produces volumes, it could produce planes, it could produce lines, it could produce a point, or it could also produce a null object. In this particular case, the example shown, I have just shown the example where the example shows that you have a common intersecting volume like a rectangular parallelepiped, but you can visualize, if I keep sliding B more with respect to A, the common volume will start shrinking in size, and at some point I have a plane, I can have a line or a particular point. We look at an operation called a difference between A and B. A minus B is the difference operation. Here what I have done is, I have taken the solid A and I have taken the solid B and positioned in such a manner that the lower right volume portion of A is the same common volume as the top left portion of B, and if you do that and subtract from A the common part, or the basically the intersection between A and B, subtract that portion, you result in a difference operation. As you can see, that white volume portion is the part of B which is basically common to A, and if you will result in this structure A minus B as a difference operation produced by this. So, this is another operation, the difference operation. You can visualize a difference operation as you produce an intersection first between the two solids A and B and subtract that common part from the structure of A. Okay. So, this is how you can produce another type of a structure using the difference operation. So, I hope you will be able to visualize. Again, I repeat again, the relative positions of A and B will dictate the resultant volume which you will get in the difference operation A minus B, as you would have got in the intersection volume of A and B. Okay. The relative positions of A and B as was dictating the intersection volume, resultant volume due to the intersection operation A and B. Also the relative positions will also dictate what you will get by the difference operation. So, these are the two operations. Of course, you can visualize what is going to happen in the case of a union. Union will be the aggregate sum of the volumes. Okay. So, if you have A and a B next to that, or with the common part or just even adjacent, the total volume integrated with what you will have as A and B put together, and of course, again the resultant volume which you will get, a resultant solid structure or the volume which you will get as the result of a union operation basically is dictated by the relative locations of both A and B. Okay. So, you have seen three operations out of, I have illustrated only two. If you have understood these two, the union operation is easy to visualize between two regular solid structures. So, with the help of these cubes you can generate other solids, and then you can actually keep generating more and more type of complex structures with the help of this. As for example, in this case you could use A intersection B along with the A minus B, or the difference between A and B to produce more complex structures by positioning them relative with respect to each other, and then creating either union, difference, union, difference, or intersection. These are the three Boolean set operations on solid structures. In this case, of course, you have seen we started with cubes, but as you can see that the resulting structures which you are getting are solids, but they are not cubes anymore. So, you can create more and more complex structures with the help of these Boolean set operations. And when we move into constructive solid geometry, we will see how with the help of these Boolean set operations we can create a few more complex structures. Okay. Now, what is the process of regularization? Okay. And the question is, why do you need regularization in a solid? Okay. You, as I said before, with the help of operations such as intersection, you could have hanging points, lines, or even surfaces of solids coming out due to Boolean set operations. I was talking about this operation called intersection, where you put A and B adjacent in such a manner that there is a common plane, or you could have a common line, or you can have a common point. If that is the case, that is not a solid, because a line or a single surface or definitely a point cannot enclose a volume. It cannot bound a particular solid. It cannot create a solid with the help of one or even two. Two surfaces or lines or points cannot create a solid, or you cannot define a solid with respect to with the help of just one or two points, lines or surfaces. And in reality, of course, there is no question of a single surface or a single point or a line hanging in the free space, and you need to represent such a typical, because when we are talking of solids, so we talk of these are structures or volumes which are bound by surfaces. Okay, you definitely need more than one or two surfaces which bind. So, if there is a result of any operation, Boolean set operation, mostly the difference operation or the, let us say, the intersection operation may produce an isolated point or a line or a surface. You do not need to keep that, because either if it exists along with a solid structure or without, it cannot exist in practice. So, you need some regularization operations on Boolean set operations to remove these hanging points, lines and surfaces to create an ideal solid which is bound by surfaces. Okay. So, we need these operations, and that is what we are talking about, regularization here. And if you look at the structure here, I have produced A operator star B, where I will say the star indicate that it is a regularization operation, whereas in the right hand side, if you see, I have used an operation A op B, where this op operator basically is a Boolean set operation without regularization. So what we have discussed earlier are operators, intersection, union, difference, which are operators, Boolean set operators, but without regularization, because these produce hanging points and lines and surfaces, and we need to implement regularization on this, which will help us to produce what we call as regularized Boolean set operation. So, let us see with this example. Let us say the left hand side is an object structure which is produced with the help of some operator which is non regularized, and we have a solid structure, but in addition we have a hanging line, or it could be a hanging surface, and also we have an isolated point here on this object. So, we need to remove these two and get only this object structure. It may exist with a hole, there is absolutely no problem of a solid structure having a hole, but it should not have this hanging line or a hanging surface or a hanging point. Of course, in this case I am asking you to visualize this in 2D, but you can visualize this object also in 3D, that as if this is a cylindrical concentric cylinder, okay, where there is a hole in between. So, we define an operation called an interior on the resultant operation on this object produced by A operated on B, and that produces this object on the left hand side, and then we have this interior operation. This interior operation is the one which helps to remove what we call as boundaries of objects. Boundaries are certain surfaces which I will say is common to the set of points defining in the object and the complement of the object. Complement of the object is the space outside the object. So, this is the surface which will be, I will say, as common to the object and its complement to the object. So, that is what, if I use to define a boundary, then an interior operation is an operation which will throw away these boundary points, and that will help us, as you can see, to throw away all boundary points, including the boundary of the object itself. And of course, the hanging plane on this line goes, and of course, what will happen is this isolated point will go, but it might create a small hole here, because we are looking at interior operations, which is this object minus the boundary. So, any points or lines which are defined as boundaries on this object are removed to create this interior point. So, of course, we may have two holes, but this object is with as boundary. And now, what we do is we implement a closure operation after the interior operation, which will restore this boundary back. Both the interior and the exterior boundary is so the closure operation is the operation after the interior operation, which defines the boundary and defines an exterior. I am sorry, it takes the solid structure and defines the boundary. It includes the boundary or attaches the boundary on the solid structure. So, if you have a small hole which is just the boundary points around, and if it does not exist in the structure, those boundary points will be added and it will be created as an interior part. So, this closure operation will include boundary points. It will also close the small hole or gap which exists due to this isolated point here. So, the regularized Boolean operation, as you can see, is a successive operations of an interior operation and a closure operation. I would request you to go to books and see a few more examples of regularized Boolean set operations. This is picked up from the example from the book by Foley, Van Dam, etc. And so, I repeat again, regularized Boolean set operations followed by interior and closure. I repeat again, Boolean set operations, union, intersections or difference. We had seen the three examples, and followed by interior and closure operation implements what we call as the regularized Boolean set operation. So, this is how we create solids, which is a valid solid now, because that solid will not have hanging points, it will not have hanging lines, okay, in the object, and the object will be closed by the bounding plane. So, this is an example of how you implement regularized Boolean set operations. We will move to the next representation of a solid, which is the sweep representation. The sweep representation is a method by which you can generate solids with the help of 2D outliers or 2D structures. Okay. In this particular case, I imagine you to visualize the left hand side structure, which is a circle consisting of a set of points on the circumference. So, you define a set of points on the circumference of a circle, which is not a solid, it is just a circle, it is just a 2D arc, a circle. So, you have just the circumference and you have a set of points in the, for the time being you assume that these points are uniformly spaced, and then what you have to visualize is I take an axis, a vertical axis passing through the center of the circle, and I now rotate this 2D circular arc in 3D about this axis. I hope you remember 3D transformations of rotation. Okay. When we talk of rotation, we defined an axis of a rotation and then an amount of rotation about that axis. So, now what we do is we have taken a 2D circular arc, just a set of points around the circumference, that is what could represent the circle. You can visualize that these are the points generated by the Bressenham's midpoint circle algorithm. Remember midpoint circle algorithm, midpoint ellipse, midpoint line. So, out of those three, think about the midpoint circle algorithm. So, as if you have generated a set of 2D points lying on the circumference of the circle, and now you visualize an axis, a vertical axis, say the z axis about which you will rotate this particular structure, and then what you do is you rotate it by a finite amount of steps. Okay. So, you take the circular arc and rotate it by a small amount delta theta, and then get these new points in 3D, the new location just toward the set of new points which this points on the arc of the circle will create. Okay. Rotated by another amount, the same amount delta theta again, and then stored all these amounts. So, if you visualize, what will happen is these points, as you keep rotating, of course, you need to rotate just by about pi radians or 180 degrees in steps, of course, of a small amount. That small amount could be 5 degrees, 10 degrees or even 30 degrees, as large as that, but typically to get better resolution, it is better to have incrementally small amount of rotation by theta. It could be as low as about 1 degree or even half a degree, let us say. So, what it means is now, although you have taken points on the circumference of the circle which is in 2D, you have to visualize that this circle lies in a plane in 3D, which could be the zx plane or zy plane. Assume a zy plane and the circle is lying in the zy plane because it is in 2D, and when you rotate this circle in 3D just by a small amount delta theta, a small rotation which you give, what will happen to these points on the circle is it will go and lie in a new set of, it will create a new set of points in 3D which will be different from its original position. So, store these points, and these new points which will be generated are new vertices of which will be used to represent this sphere. Again you rotate by another amount and keep doing this till you have rotated in steps, as you can see here, by about 180 degrees, up to 180 degrees, not in steps of 180 degree. You need to increment by delta theta, 2 delta theta, 3 delta theta, and so on in steps, and you stop when the total amount of rotation which you have given to this 2D structure is 180 degrees. What will result in? At each point after rotation by delta theta, you need to store these 3D coordinates of these points which you have created on the circumference of the circle. And when you create that and you store those points, all those points after all those rotational incremental rotations, when you store, you have basically got the points on the surface of a sphere. You have got the points of the surface of the sphere. If you look back, this will be the resultant sphere which will be generated by giving this 2D circle a sweep or a rotation about a 3-dimensional vertical axis. Of course, you can rotate about any arbitrary axis, it could be a horizontal axis or it could be an inclined axis, does not matter. You will still, you are creating an operation which I have just described, is called the sweep operation, and with the help of the sweep operation, what you have created is a set of 3D points, a set of 3D points on the surface of an object, and these set of 3D points are nothing but the vertices of those polygons which will enclose this particular solid. In this case, you have generated a sphere from a circle. So, you need to sweep any arbitrary in a general case, when you talk of a general case, you can visualize any arbitrary two dimensional structure or a polygon for that matter, and when you talk of a sweep, you can rotate with respect to a particular three dimensional axis, you can translate it, you can give it any sort of transformations which we have studied in under three dimensional transforms category. Okay. You can give a combination of transformations, typically a rotation and a translation, a rotation and a scale, or you can actually sweep it along any arbitrary line or a curve or an arc, or just simply apply rotation, which we have just seen, which in this case which helps you to create a sphere from a circle. A sphere from a circle is the best simple example for you to visualize. It is something like if you can create a circular ring and hang it with the help of a rope and just simply give it a twist, you can almost visualize that when the ring spins, it will create an impression of a volumetric structure of a sphere, and the bounding surface, the spherical surface will be traversed by the arc of that particular ring which you will be spinning about that axis. I repeat again, imagine a ring created by a simple thin iron rod or even a stiff rope type of a structure if you can visualize, but an iron ring, let us say take a large iron ring with the help of a iron wire, create a ring, suspend it from a string and then give it a rotation. Okay. If you give a very fast rotation or a spin, it will create an impression of a spherical structure which you will get. What it basically means, that is the reality which will happen in computer graphics literature for sweep. In this case, to create a surface from a circle, what you are doing? You are taking points, Bressenham's algorithm for midpoint circle algorithm. You remember that? Take points on that arc, and at each step give it incremental rotation, and at each point of rotation you just note down or store the points on the 3D points on the arc of the circle in 3D, because at each point when rotating in 3D you will get different set of point x, y, y, i, z, i. For each point x, i, y, i, z, i, after you rotate it will go to a new point x, i prime, y, i prime, z, i prime, give it another rotation, that point goes to x, y double prime, x, y, i double prime, z, i double prime, and so on. And this is true for all the points I on the circumference of a circle. As you keep on rotating, this is what you will create. And here I have shown the arc of rotation. Its rotation could be in any direction, there could be any arbitrary axis. I repeat, in this case I have taken a vertical axis, but you can take any axis, and this is the structure of the sphere which you will be generated. If you look at this structure, you would have seen this type of a structure at many places, not only in computer graphics literature, but you could have also seen that in the case of the map of a globe. When you talk of latitudes and longitudes in a global map or in a globe type of a structure, then what you will basically have is latitudes and longitudes. Latitudes and longitudes are parallel lines parallel to the equator which never meet, and then you have the vertical arcs which basically intersect at the north pole and the south pole of the particular solid. Okay. So, this is what is created by with the help of the sweep representation for a circle in the case of generating a sphere, and the vertical lines, the circles intersect at the north and the south pole in the case of a globe, and of course, you have horizontal lines, concentric reducing circles which keep reducing the radius as you move towards the north or the south pole. Imagine the case of a globe. That is a very simple example to visualize this with the help of a globe structure, and that is what is an ideal example of a sweep representation to generate a sphere out of a circle. Now, the question is, what should be the radius of the circle which you choose to generate this sphere, and how much is that value of delta theta which you have to select to give it incremental rotations as you keep on sweeping? Well, that depends upon two aspects. What is the size of the structure which you are generating? That means the radius of the sphere is in this case simply going to detect the radius of the circle which you need to choose. That is very simple and straightforward. The other aspect is, what is this delta theta? Well, the lesser you choose the amount of the delta theta value, you will get more amount of set of 3D points which will enclose the sphere, or more number of polygons which will enclose the spherical surface. If you have if you choose a larger value of delta theta, you will have lesser amount of points and hence lines and lengths polygons, polygonal surfaces which define the spherical surface. The more higher degree of resolution you want, the greater degree of approximation you want, because what is happening in this particular case is, if you even take a, let us look back into the slide, if you look into a particular small area, a set of 4 vertices which will enclose, keep watching my mouse at it as it keeps pointing to 4 different vertices which will enclose and give you a particular polygonal shape. Those 4 vertices will actually create a polygonal shape. So, it will create a plane, and at that region, that plane is going to approximate that part of the small spherical structure or the part of that sphere or the surface of the sphere at that region will be approximated by that polygon, and polygon is always a plane, and all parts of the sphere is a curved object, it is never planar. Sphere surface is always a case where it is never a planar surface, it is always curved. So, at any point of time you are always approximating a section or a small part of a curved structure, in this case of course a spherical surface, by a planar shape or a plane or that polygon. Okay. Now, how close you want to have your approximation depends on how much you can afford, because you can take a very small amount of delta theta. What will in fact happen is this polygonal approximation area will become smaller and smaller, and you are having a greater degree of approximation, but at what cost? The cost is that you have to store larger and larger number of vertices and lines which are used to represent this solid in the case of a sphere. So, if you want a very good approximation, that means the more closer to the curved object which you need to represent, more smoother approximation which you want to do, then you have to go for smaller amount of delta theta, larger values, smaller amount of delta theta for the sweep, which means larger number of points and lines you need to store for the to represent that object structure. Whereas, if you can't afford, if you cannot afford a larger space for storage for your solid structure, because you need to use the solid structure for various other operations like create various other operations, complex structures with the help of Boolean set operations. Then you need to of course find out what is the shading, so that you can shade the surface with certain color. We will see these when we talk of shading models or visible surface determination algorithms, we will talk of those, and they could become very complex, and you need a lot of computation time when the number of the polygonal surfaces increases quite a lot. So, the storage is a requirement, and that also enhances the computational time. Whether you can afford that is the another question. So, all these will dictate the amount of smoothness or coarseness. When you talk of coarseness, I am talking in this particular example larger values of delta theta, which will create lesser number of points and lines to represent and store for this solid object, and in that case that will reduce the number of computations required for creating higher level complex structures or even shading this particular object, but the object structures will require very coarse. It will be a very crude approximation, low level approximation of this curved object. If you can afford it, if you want it, it is fine, but if you want if you can afford greater amount of storage, if you have computational storage a lot of it available, if you can afford a lot of computational time in your system, then you will have to have a very good approximation done based on your application, and then you have to have small values of delta theta. This is true for any sweep. We will see for other examples of sweep representation. I am just asking you to concentrate on this particular case where I have generated a surface. It is a volume from a sphere has been generated by sweeping a two-dimensional structure, which is in this case a circle. A circle is swept to generate a sphere in this particular case, and if you can afford, if you have larger amount of complexity in terms of storage space as well as computational time as the requirement says, then in your application you need to have a very good approximation of the curved object, and that can be only done with smaller strip sizes of your delta theta in this particular case. So, it is a compromise between the approximation or the fineness, the resolution you need to represent the object and the computational time requirement. So, you better choose whether you can go for a finer resolution and then choose smaller values of delta theta. If you can't afford it, then you make your delta theta much more larger and have a coarse approximation. So, we move forward to look into other applications of sweep representation, and I have just a few more examples for you generated to visualize the sweep representation, but I hope I have sufficiently described how do you represent an object using sweep. These are some more examples of sweep representation. There are 3 different structures being talked about. In the first left example, I have taken a simple triangle and the sweep is just a straight line, an axis in 3D along which I translate this object. Okay. So, that generates a sweep. So, you can visualize that I have these 3 structures. This structure 2D structure is a triangle with 3 vertices, and as I keep sweeping along a particular direction or a vector in 3D, I can do it in steps, fine steps, more complex structure in terms of the number of space requirement, and I can have larger displacements where it results in a coarse structure and lesser number of points to store. I can afford to do this in this particular wedge type of a structure generated by a triangle, because I am approximating planar surfaces. When I am representing planar surfaces with the help of a sweep, in fact, I can go to a very coarse approximation where I can afford to take the first position of the triangle and the last position of the triangle, and I do not take any positions in between. So, I sweep from a starting position to a finite to the finishing position or the end position, and I can still define the structure, because in this case I am representing a solid which is bound only by planar surfaces or planes. When I am representing curved surfaces, curved structures, surfaces bound by curved surfaces rather than planar ones, I have to go in for a finer sweep representation, finer representation, and then I have to sweep in steps, maybe in finer steps if the curvature is more for this solid. If the curvature is slowly moving or it is a plane, the step size could be larger. So, come back again here, as I was saying that in this particular case of the wedge, I can have the starting point and finishing point, that is just sufficient. That is not true for these structures. Of course, in the structure on the right hand side, which is still the sweep direction is a line, I can have the starting point and finishing point, but that is not the position, that is not the case in this arbitrary structure. As you can see, a bony type of a structure where when I am sweeping, I am not only sweeping along a curved line, but I am also giving the structure a scale. So, it is a simple example where you can visualize I can create a cone also with the help of a circular structure. When I sweep along the along an axis which passes to the center of the square, assuming an axis passing to the center of the square, I sweep along that, I will get a cylinder, but when I scale up or down, I will get a conical structure. Okay. So, in this case I can generate various types of solids with the help of this structure. These are the third case example. The largest one in this case is an arbitrary structure chosen and dragged or swept along an arbitrary curve, and when I am sweeping along this curved line, I am also giving it a scale. I am increasing it larger and larger, giving it a zoom, and I am expanding it out, and that is what I create. Okay. These are certain examples. Again, as I was taking, you can create a pyramidal structure with respect to this with the help of this square structure. When I am sweeping, I give it a zoom, I can create a simple cone. This structure is a very simple example of like a conical ice cream, where I can have this, but the structure is a cone where I can take a circular structure, sweep it along an axis which passes to the center of the circle, and when I am sweeping, I give it also a scale or a zoom. And I can also have an arbitrary path for this sweep. That is also possible. Nobody says that you have to sweep only along about an axis and then sweep a circle to create a sphere, sweep it along an axis passing to the center to create a cylinder or a pyramid or a cone and all that. To create very irregular structures, I need to have two combinations, a combination of a path or a sweep which could be very arbitrary, not only along a particular axis, it could be arbitrary, it could be an arbitrary helical structure which we have just seen, and when I am sweeping along that particular structure, I give the structure a scale. So that if required, I can give that to produce more arbitrary structure. So a very general example is this, in this case, as you can see in the slide, that the sweep could be an arbitrary path, in this case a helical structure, and that too not very smooth, it could be very arbitrary, and you can visualize what sort of a structure which you will get. I ask you to imagine, I am requesting you to imagine a structure which will be generated when I am taking a circular a circle in 2D, take a circle in 2D and then sweep about another circular arc in 3D. Let us say the circle is in the xy plane, okay, assume an xy plane, the front in your monitor, the xy plane, z axis is going towards you, okay, an xy plane, and assume a circle in this xy plane, and I take a circular arc based on which I am sweeping, and that is in the zx plane. Z is towards you, x is on the right hand side, y is the vertical axis, let us say. So assume a circular sweeping arc, the path of the sweep to lie on the z x plane and the circle in the xy plane. So if I provided a sweep along this, you can visualize that I have a ring type of a structure, but I get a structure which is called a toroid or a torus. Okay, so that is the structure which I can. So I can generate various types of models using sweep, both regular and in fact very highly irregular structures. The only thing which I must have is I should be able to represent as arbitrary solid with the help of a sweeping arc or the path of the sweep you have to define, and also you must define the structure which you need to sweep. In fact, for the structure which you need to sweep, then the path along which you need to sweep, and then when you are sweeping the structure along the path, whether you need to give other transformations like scale. Okay. The path could be a simple translational path or a curvilinear path based on a rotation or a combination of rotation and translation, it could all happen, and you can provide scale and shear as you move along the path. So these are the combination of these 3D transformations which we have seen earlier is all coming back, which is necessary now to provide these sweep representations. Okay. So this is how you provide sweep. I have just given one example with the help of the circle and the sphere, but I have given also other illustrations of pyramid, the cone, the wedge, and I have of course visually asked you to imagine the case of a torus, and of course other arbitrary structures, one or two examples I had given. So this is how you generate, and what do you store as an output of the sweep representation is the case when you store the xyz vertices generated by the sweep of that structure. Okay. So that is how do you generate solids with the rest of the help of sweep. In the remaining time available to us in this lecture, as we continue solid modeling and constructive solid geometry discussions today as well as in the next class, we will go to the next representation, which is probably the most popular method of representing solids, called boundary representations or B-reps. Boundary representations or B-reps, we talk of an object which is defined in terms of surface boundaries, vertices, edges and face. This is nothing of course new, because when we talked of a solid is also defined and it is bound by surfaces, and the surfaces are again defined in terms of edges or faces, and edges and faces are again defined with the help of vertices. So we know that. Okay, but this representation is different than the case of sweeps. So curved surfaces are always approximated with the help of polygons. So we talk of piecewise, linear or planar approximations of curved surfaces with the help of boundaries, and this is very commonly used in practice. So this is nothing new. We talked of this solid object in the case of a cube, which is defined with the help of surfaces. So there are surfaces which bind this particular solid. On the top, we of course in the cube we had two surfaces, one on the top and the bottom, two on the left and right, two on the front. There were about 6 surfaces, and there were 8 vertices if you remember, and there are about 12 lines which define. So I try to imagine boundary representations closer to that particular case of a cube, where the cube was bound by certain surfaces, polygons, lines, edges or vertices. We use the term faces also here to represent the solids. Okay, and unless in the case of unlike in the case of sweep representations, where we used a sweep to represent curved objects, here in the case of boundary representations we always go for a piecewise, linear or planar approximation. Sweep also does that, I must admit here, but always in this case we are talking about polygons which approximate curved surfaces as well. Okay. So we use planar polygonal boundaries, but may also use convex polygons or triangles. to represent in the case of B-reps, and we define a new term based on which we on polygons, where we define the term called polyhedron. A polyhedron is a solid that is bounded by a set of polygons whose edges are each a member of an even number of polygons. This is interesting, we will see, and we will discuss of additional constraints later on in the class, but we will wind up the lecture here today with the discussion of what is called a polyhedron. So, that is a new term which we use to define a solid under the category of B-reps or boundary representations of solids, where we say that a polyhedron is a solid. Of course, it has to be bounded by certain surfaces. It is a solid that is bounded only by a set of polygons, and those polygons are again defined with the help of edges, and those edges are each a member of an even number of polygons. So, we say that we can have edges all right, which define the polygons. Polygons are the planes or faces which bind the solid, but in this case we put a first restriction which we put is that each edge of such polygon should be shared, or it must be common to more than one, not only more than one, but we should have an even number of polygons. We will see how that constraint can be holds good with the help of examples when we visit the next lecture on the solid modeling after this, but here we again wind up the lecture today with the definition of a polyhedron once again, where we say that polyhedron is a solid that is bounded by a set of polygons whose edges are each a member of an, remember this, even number of polygons. Edges are each a member of an even number of polygons, and that is the first constraint we put on boundary representations. First constraint we put on boundary representations. We will see other constraints with respect to the edges, that is the lines of the polygons, and also the surfaces of the polygons and the vertices. We will put additional constraints to define what we call, remember the beginning of the lecture, a valid solid. A valid solid should have certain constraints based on which we can say that is a valid solid object and not an open or an enclosed one, and that constraints we will define with the help of planes, lines, edges and vertices. The first constraint which we have seen today for the polygon is that an edge must have or must be shared by an even number of polygons. We will look into additional constraints later on in the next class when we meet to discuss further on boundary representations for representing solids. Thank you very much.